understanding physiological and metabolic pathways of algal isolates from Yellowstone National Park, which it is hoped can be used to improve biofuel production for real-world applications. So we're very excited to have you, Muneeb, and I want to remind everyone that this webinar is being recorded for posterity, and it looks like everybody's in line on mute for now, and then hopefully there'll be plenty of time for questions and answers at the end of the talk. So take it away, Muneeb, and thank you so much for being here.
Thank you so much for that introduction. Good afternoon, everyone, and thank you for coming. Let me just share my screen. So my name is Muneeb Rathore. I come from Pakistan, a chemical engineer, and I work with Dr. Brent Payton in the Environmental Engineering Lab at MSU. Today I will be talking about algal biofilms for biofuels. So what are algal biofilms? To begin with, algae are eukaryotic photoautotrophic microorganisms. They use sunlight and carbon dioxide in the presence of a nitrogen source, such as nitrate, to make biomass, do cell replication and cell maintenance. In this process, where algae is growing and accumulating useful nutrients, we can get useful products from algae that can be lipids, astaxanthin, carbohydrates, proteins. We can also use algae for water remediation to remove useful nutrients such as phosphorus or nitrogen. But then what are biofilms? So biofilms are aggregates of cells that are attached to a substratum, and they use extrapolymeric substances, which are macromolecules of sugars, abbreviated EPS, and I might throw that term out a number of times later. And so these aggregated cells, they perform all their physiological functions on attached on that substratum, and they give us an advantage of concentrated biomass. Why are we interested in algal biofilms? We have to look at the U.S. energy consumption, and the sources of energy that the U.S. currently has or uses. There's a summary presented here. Petroleum accounts for about 37% of U.S. energy consumption, and renewable energy is standing at around 11%. This is data from last year, and out of that, biofuels from biomass make up a small percentage, around 20%. And this biomass is conventional biomass from conventional agricultural crops. So why are we looking at the energy consumption? Because of the CO2 emissions. And petroleum accounts for about 43% of CO2 emissions into the atmosphere, just from US alone. And that can account for about 2,400 million metric tons of carbon dioxide, which is a major issue because CO2 is a major contributor to climate change. Whereas coal and natural gas are about 34 and 22% respectively. And climate change can cause food insecurities as well as adverse climate effects and weather patterns. One source of mitigating that CO2 and looking for alternative fuels is algal biomass. And algal biomass is important because, as I said earlier, algal biomass can make lipids, and that lipid can be converted into biodiesel directly. using certain chemicals. And it says that biodiesel can replace diesel from petroleum-based fuels directly. Why would we want to still grow algae? Well, because when you compare it to oleaginous crops, conventional oleaginous crops, algae is amongst the highest yielding crops when you look at the amount of biodiesel that you can get from a particular land area over the course of a year. So it is the most advantageous biomass source. Literature has shown that an algae cell can have up to 80% lipid of its cell mass in terms of ash-free dry cell weight. So you remove the inorganic content and then you measure this percentage. And that lipid can provide you an even higher yield. This table that I show is from a day that is earlier than this study, about 80% biofuel potential was published. Also, another advantage of algae is that you can use low quality water and low quality low quality land to grow your biomass. And how does this biodiesel production process work? First, you have to grow your algae. And you have to pick a reactor system. It can be open to air, it can be closed system, and you have to provide adequate nutrients and artificial or natural light for the algae to grow. And once your biomass has grown and accumulated enough lipids because of some nutrient stress that you provide, or just they run out of their nutrients, you would have to dewater and dry that algae so that you can extract the lipids and convert those lipids into biodiesel using transit esterification or other processes. Now, the dewatering and drying step can increase the cost of the biodiesel that you produce from algae. And the dewatering cost can be up to 30% of the process costs. This is a metric taken from another fellow graduate student who visited MSU a couple of years ago and did an economic analysis on biodiesel production from algae. And he also gives a metric of $10 per gallon biodiesel cost from algal biomass. So that presents a problem when you want to grow your algal biomass. Which brings us to the objectives of what I'm going to talk about today and the studies that I did subsequently. So our first objective is that we want to grow algae as biofilms so that we can obtain concentrated biomass to reduce the water content removal requirement so that we can lower the cost. I do not do economic analysis. I just do the physiological study. We're trying to grow algae as biofilms so that water costs are reduced for biomass processing. And then the second half of my talk would be about improving lipid accumulation in algal biofilm systems. And doing an extensive literature review, what I found was that when you grow algae in suspended cultures, planktonic growth, they fare well when accumulating lipids, and they do not do so well when you try to grow any number of algal strains that others have studied as biofilms. And in fact, they can even reduce the biofuel content or lipid content when you try to stress subject algal biomass to nutrient stresses. So what others have done so far, and these are just the top three studies that I like, and there are others out there that have looked into algal biomass production as biofilms for biofuel. So I present four pictures here, and the table essentially summarizes what these researchers did. There are three types of reactors as shown in plot A. In figure A, you see the rotating algal biofilm reactor, and the lipid content, the maximum lipid content that they showed was up to 22%. In plot in figure B, you see the lab scale version of that rotating algal biofilm reactor, and the 22% metric incorporates that. It's actually from that study. In figure C, you see the algal turf scrubber, and that is used mostly around farmlands and near coastal areas by Sandia National Labs to remove nitrogen and phosphorus from agriculture or wastewater runoff before it goes into a major water body to prevent harmful algal blooms downstream. And in figure D, you see the flat plate reactor, which is from a researcher in Canada, Peter Snore, and the lipid content that he presented was around 4 to 7% using a nitrogen stress. So another aspect that before we begin our studies, we have to look at what algal strains are out there, and what strains did I use and why did I select them. So I chose to do my studies on two algal species. One was a green alga, Chlorella vulgaris, and it is among a model microalgae. Its genome has been sequenced. It has a high growth rate. It has a high growth rate and a doubling time that is approximately 15 hours. In the figure on the right, you can see Chlorella vulgaris cells showing up as green circles, and they're actually in an aggregate. And also, one advantage of Chlorella vulgaris is that it's oleaginous. So I wanted to use a model organism that is well understood so that my biofilm studies would be easier to do, so that I can learn biofilm physiology and then move on to something more complicated, which is the diatom RGd-1. And the focus of my talk would be around physiology rather than any bioinformatics or transcriptomics. That would be in the future works that we will do in the lab. So the diatom RGd-1, it is a Yellowstone National Park isolate. It was isolated by one of a good friend of ours, Rob Gardner, from Yellowstone National Park's Witch Creek, and it is an extremophile. It grows in alkaline environments, and it is shown by another PhD candidate in our lab, Karen Moll, to make the highest lipid, to be among the highest lipid producers that are out there, to the best of our knowledge. And you can see these silica frustules. It does not have a cell wall, a cellulose-based cell wall. It has a silica frustule, which houses the cell. And in this electron micrograph, which has a scale bar of 1 micron, my apologies for it being too small, but which has a race in the middle and then pores in the silica frustule for nutrient ingress. and another PhD student in our department took this picture for me, Sobianju. This is a picture showing the location of Ridge Creek. This is approximately where we found this diatom from, and it gets alkaline hot springs water, which provides an extremophilic environment, and this extremophilic alkalophilic environment can provide a defense against detrimental microorganisms that might want to harm the algae, but may not like alkaline environment to grow. As to do our studies, we found that there was a need for a reactor with an integrated harvesting mechanism. And this is just a block diagram, a flow diagram of what our reactor does. Essentially, it is a packed bed reactor with light coming in from the top. It is abbreviated as ABR for Algal Biofilm Reactor. And sterile feed with nutrients comes in from the top. And while light comes on the top, biofilm grows on the top layer of our packed bed, which we use silica as our packed bed. And then there's an overflow, which takes away excess liquid media to prevent overflow, of course. And we also, since we cannot agitate our reactors because we want to maintain our biofilms, we take out the media from the bottom of the reactor. We reintroduce it at the top to provide adequate mixing inside the reactor. And the dotted lines show where we need to use air for our studies. We connect additional equipment. This dotted line at the bottom with the arrow going into the reactor shows when we need to harvest our reactors, we use air, which is a novel method of biomass detachment, algal biomass detachment that others in the past have not used before. When our studies required carbon dioxide from air, we would introduce that in a separate system by taking the nutrient media into that system that we call the sparger, and we would aerate that sparger and reintroduce our media right at the top. This is our reactor, which is designed by myself, Dr. Brent Payton, Dr. Garlog, and Karen Moe at the Center for Biofilm Engineering. This is what that reactor looked like in operation. And in this picture, we're actually growing Chlorella vulgaris biofilm. And the green color that you see is, this is at the time of inoculation. So you see a lot of green in the suspended phase, which is above the substratum, which is our silica. We cover it with glass petri dishes. We try to make it as cheap as possible and as easy to maintain as possible. We used a Buchner funnel, which was made out of polypropylene, so everything can be autoclaved, including the tubing. Here for that very reactor, I have removed the water. When I am doing biomass harvesting, I remove the water and I add a known amount of water again, but about 20 to 50% less than what was in the water to begin, what was in the reactor to begin with, so that I can get an even more concentrated biomass suspension. What you're looking at is Chlorella vulgaris growing on a silica bed, and these tiny particles are silica beads, and the green in the image is algal biofilm that is attached to those silica substratum. And since we need to look at the reactor performance based on previous literature, we didn't have data to operate the reactor until we operate the reactor and we know how it performs and what we need to do in terms of flow rates. But based on previous literature on suspended cultures, we estimated flow rates of our medium by scaling the growth rate down by a factor of 10 to 20%, because according to the standard Biofuels methods lab at MSU, when cultures are growing as biofilms, they will have slower growth rates. So to prevent prevent washout by the media, washout of algal cells, we choose a very low flow rate of 0.2 milliliters per minute over fresh feed, which is both 8.7 freshwater medium, since both of these algae are freshwater algae. For our studies, we just used bowls and modified it a little bit for diatoms. We used a 14-hour night, 10-hour dark diel cycle, and our recycle flow rate was set at 5 milliliters per minute. And at the time of biomass harvest, we would use aeration to detach our biomass, but we would cut off all flow of media in and out and recycle before we would do that. Which brings me to my first study that I did here, which was Chlorella vulgaris biofilm growth in the algal biofilm reactors. Our objective for this study was to provide enough inorganic carbon and as much of advantage to algal cells to grow as a biofilm as possible. So we looked at different inorganic carbon sources or regimes, and we looked at calcium as a attachment facilitator for our algal cells. So our treatments included aeration for carbon dioxide source. We added calcium carbonate in another treatment, calcium chloride in another treatment with air supplementation. We also tested 5% CO2 pH control. pH control was done because you don't want to continuously add carbon dioxide. It would lower the pH too much. So you would let the algae grow and only add carbon dioxide when a certain pH has reached, a certain alkaline pH has reached to facilitate extra carbon dioxide dissolution. Excuse me. And we also looked at adding extra sodium bicarbonate, and bicarbonate has been shown in previous studies by the researchers to improve algal growth rates. And we also added calcium chloride in another treatment with extra sodium bicarbonate. So the concentration of our calcium chloride and sodium bicarbonate were maintained at 5 millimolar. So here we're looking at the aerial cell density in terms of cells per meter squared of incident light, along with the time at the x-axis. So at the beginning of our reactor operation, we do a 24-hour recycle full batch system. So we do not add a fresh medium, and we do not take out excess medium. And that is to facilitate attachment, to let the algae adapt to a different growth system. And and essentially it is to prevent algal cell washout. So for our 5 treatments that I talked about earlier, the key feature here is that bicarbonate for inorganic carbon source, and bicarbonate with extra calcium added reached the highest cell number around day 5 or day 6. And other treatments also followed suit, and they reached that cell number later. But when it came to air with 5 millimolar calcium, I think what happened is that since we were giving inorganic carbon from air, and we had 5 millimolar calcium present in our systems, the calcium would precipitate with carbon dioxide coming in into the aerator, and at some point, algae would not have adequate inorganic carbon to continue to grow, so their cell numbers flattened out. Another feature that is very important to remember here is that you're looking at a system that has continuous inflow of nutrients and continuous, although it is a very low flow rate, and continuous removal of excess medium. And so in the biofilm processes, since these cells are attached to the substratum, they can also detach from the substratum and get washed out. And this attachment detachment can happen continuously while the cells are growing on the substratum. So you're looking at a steady state instead of where your growth and your attachment and detachment are balancing. When we looked at the suspended cell concentration above the biofilm, and in the first 24 hours, during time of inoculation, the cell concentration was the highest. And then it decreased as the biofilm has started to form and cells had settled down. And throughout the course of the experiment, the cell numbers were they were anywhere between 10 to the 5 to 10 to the 6, and the only thing I could say here is that there were cells present in the suspended phase all the time, which could be due to growth in the suspended phase itself or detachment from the biofilm. So here, the idea that I gave earlier about air and 5 millimolar calcium condition is kind of reinforced. What you're looking at is pH on the y-axis and time on the x-axis. And you notice that when carbon dioxide from air is coming in, algae is growing, the pH actually starts to decrease in the air with 5 millimolar calcium condition in this empty square dotted line. But for other conditions, the pH increases as algal biofilms are growing. And as algal biomass grows, it fixes carbon dioxide. So in the resultant biochemical reaction, there is a hydroxyl ion that is left behind, and that increases the pH of our systems. And pH is a good indicator of algal biomass growth. The highest pH increase was observed with 5 millimolar bicarbonate condition, and the same was not observed for 5 millimolar bicarbonate and 5 millimolar calcium condition, and I think that is likely due to precipitation of calcium. And here we're looking at how well our detachment method worked. And on the y-axis, we have the dry cell weight, which is all the water is removed, and all the biomass is filtered, and that biomass mass is measured. On the x-axis, you have initial and final detachment for these 5 different conditions. And and what does initial detachment means? It is the aeration-based biomass removal from our substratum, and the air flow rate that we use for that purpose was 1 liters per minute, and that was for around 10 minutes, and actually 30 minutes sometimes for some conditions, because we would start aeration at the same time and then start harvesting the reactors from one end to the other. And by the time we would reach the others, more time would have passed. So not really 30 minutes, we were quick enough. And the final detachment means after aeration, the remaining biomass that was attached on the substratum, that substratum was sonicated in additional water to see how much biomass remained and did not detach with aeration. And our aeration-based detachment was from anywhere between 40 to 70%, and the maximum biomass that we obtained was with the 5 millimolar bicarbonate and 5 millimolar calcium condition. And then next was the 5 millimolar bicarbonate condition, but it was fairly close to the others as well. So one metric that the algae industry uses is productivity in terms of grams of biomass per square meter of incident light over the course of the growth. And we wanted to see that how much of our biomass that we had measured earlier, dry solvate, was actually just inorganics and ash content, and what would be our actual productivity of biomass itself. And this is where the 5 millimolar calcium condition with additional bicarbonate is shown to the extreme right of this plot. And our ash-free dry solvate, abbreviated as AF-DCW, is around 0.75 grams per meter square per day. And if we do not account for the ash content, we get an overestimate of productivity. And you can see that the average is around 1 gram per meter square per day. All these other bars are standard deviation plotted with averages. So another thing that we tracked was at the time of harvest, how much fatty acid, methyl, esters were there. Now these are the lipids transesterified, and so we give this metric as percent weight of fatty acids measured on a GCMS, which is gas chromatography mass spectrometry, with the hexane as a carrier solvent. And and then it is normalized for grams of biomass, and we remove the ash content that is present in there to give a realistic fatty acid methyl ester content and weight per weight percent. And for our 5 conditions, it was around 12 to 14%. None of these conditions were nutrient stressed. And algae accumulate lipids when they're either run out of nitrogen or some other nutrient that is essential for cell replication, and they realize that they're under a nutrient pinch, and they start to make more fatty acids, which are compounds they can used later and survived longer. Since there was no added stress in these conditions, that brings us to our next study. And a little bit of background, Rob Gardner, Dr. Rob Gardner at Montana State University in his PhD work published in 2012, which was drawn in a tubular photoreactor systems picture here. And he showed that there are advantages to adding additional bicarbonate when algae are about to run out of nitrogen. So in this plot, which is from his paper, you're looking at fluorescence intensity in terms of Nile Red Fluorescence of algal cells stained with the dye Nile Red. And what he did in his study was these arrows indicate when he added 50 millimolar bicarbonate to his reactors and changed his reactor conditions to stimulate lipid production in his algal cells. The line represents at the time when the reactors amended with 50 millimolar bicarbonate and without ran out of nitrogen. So the top line that you see with the empty squares is Nile Red Fluorescence intensity for the condition where there's nitrogen is limited and 50 millimolar bicarbonate has been added. And the bottom line with the solid squares is where he showed that there's only aeration based inorganic carbon ingress into the reactor, and nitrogen has been removed. The nitrogen has been used up around this time. And he showed that algal cells increase their lipid accumulation by at least 2 to 3 times. And one thing to note is that Nile Red estimates the TAG content, which is triglycerides in the algal cells. And what I wanted to do was the same level of awesomeness in my biome studies, which brings me to Algal Biofilm Reactor, Chlorella vulgaris, and RGd-1 nutrient stress study. Now, for the interest of time, I will talk a little bit about RGd-1, but mostly I will just discuss Chlorella vulgaris to keep continuity, and I will show you in the next few slides why I don't talk about RGd-1 that much. So you're looking at a log scale plot of aerial cell density with time for Chlorella vulgaris biofilms, and up to 13 days, these biofilms were grown on bowls 8.7 in my algal biofilm reactor system. In our reactor system, and this medium was supplemented with 5 millimolar bicarbonate. And I could have just used sparging for air, for CO2 from air, but that increases the number of pumps to an unmanageable level, and I did not have that many pumps. And I wanted to grow a lot of biomass really quickly. So hence I used a 5 millimolar bicarbonate from the beginning in the media. For the Chlorella vulgaris is a hardy microalgae, and for the first 24 hours, again there was batch, but there was some cell number increase, and the cell numbers kept on increasing until they slowed down to a, they started to flatten out after day 7 through 13. And the arrow indicates the time when I took out all the media that was present inside the reactor. And this was nitrogen replete media with 5 millimolar bicarbonate. I removed that media and I added nitrogen deplete media, and I kept one set of reactors as inorganic carbon control, and I added only air to those reactors, those set of reactors, and the other set of reactor I added 50 millimolar bicarbonate to at this switch. Another thing to note, at the time of this switch happened right before the lights were about to come on in the diel cycle. And so that I do not stress out my algae too much that they just kill themselves during the light cycle. I want them to have some time for adaptation before they wake up, to put it colloquially. And this media, after this media switch, I turned off all input and output flows. So no fresh feed was added and no excess medium was taken out after. But the 5 milliliters per minute recycle kept on going. And what I saw, as you see the cell number dip here, this is a detachment event. And algal cells don't like to be disturbed from their normal adapted state. And this is shown here in the suspended cells with time plot for Chlorella vulgaris. Around day 13, when I did the media switch, you see that the cell numbers increase in the suspended phase. Now, this is the plot for RGd-1 cell density in terms of the aerial cell density with respect to time. And I wanted to keep fluorines the same for all of these strains because I wanted to compare the two as much as possible and by keeping the conditions as same as possible. But RGd-1 did not like that. It grows even slower. It grows slow, but much slower than Chlorella vulgaris does. And what we see here is that for 5 days, essentially, it is in the DAG phase. And so the 24-hour batch should have been probably kept at 48-hour batch to give it more time to adapt and attach and grow as a batch before switching to continuous. The cell density increased just a little bit after 5 days, and then I started to see a decrease in the cell density, and that was with the algae cells washout. The flow rate of 0.2 milliliters per minute was too high for RGd-1. So for future, I used a lower flow rate based on a 40-hour doubling time, for RGd-1. And I also would let RGd-1 ABRs to stay at 48-hour batch during after inoculation. So here we're looking at the plot of pH with time for these reactors, and for the bottom two lines and are for RGd-1, and you see that not much carbon fixation happens, the pH remains around the same as the fresh feed pH, and further proving my point that algae is washed out. For Chlorella vulgaris, the top two lines here, the pH rose to around 10.7, highly alkaline. And with the media switch, there's the pH is at 8.7 of that media that I switched with, but that is recovered quickly within the course of a couple of days, indicating carbon fixation. So just like Robert Gardner, I was tracking Nile Red Fluorescence with time, and what you're looking at with the blue circle line, dotted line, is the condition where there is no bicarbonate, but also no nitrogen in the form of nitrate. And the solid black line is the 50 millimolar bicarbonate condition. And I saw a similar trend as Rob Gardner saw. And it got me thinking, why didn't others see the same trend? Others who actually visited our lab and used this same bicarbonate amendment strategy. And I will get into that in a little bit. But the key feature is that you're looking at Nile Red Fluorescence per cell on the y-axis with time. And since Nile Red Fluorescence, as I said, correlates to TAG accumulation, the 50 millimolar bicarbonate condition showed twice as much Nile Red Fluorescence almost as compared to no bicarbonate addition. And so going back to the rotating algal biofilm reactors, the studies that were done previously were done on those reactor systems with the bicarbonate and amendment strategy. And one thing to remember is that they were using cotton rope as a substratum, which would soak up a lot of the medium and would remain. When they tried this strategy, that cotton rope was probably acting as a nitrogen source and was providing nitrogen to the algae. I also did Chlorella vulgaris brightfield and fluorescence microscopy. This is the picture I showed earlier. The greens are the Chlorella vulgaris. The red that you see is Nile red dye. And the image on the right is the Nile red fluorescence. Yes, from the Nile red stain, and the yellow is showing lipid vacuoles, Nile red fluorescence. I also did FAME content %, and in a separate study, I did look at FAME content and the same strategy I just showed for RGd-1. I would take this data with a grain of salt because I used a automated method for that is on the software that is used to operate the GCMS. The FAME content is reported in % weight of fatty acids per and free radical weight of biomass. And I'm skeptical still because the automated software, it is a quick analysis technique, but I think this is an overestimate. And I'll verify peak by peak. There are too many, and there are too many peaks when in the chromatograms, and it becomes very complex to do by hand. which is the way I like to do it. So FAME content was nearly doubled with this 50 millimolar bicarbonate amendment strategy. Another thing for the future I want to look at is how much carbohydrates were present. Since starch is a primary storage compound and could act as a potential precursors to EPS production, I would like to look at the EPS content as well. So to conclude, ABRs were found to be an effective tool to study algal biofilm physiology, and our detachment mechanism worked. Calcium facilitates biofilm attachment, but also precipitates to increase ash content. With increasing bicarbonate concentrations, precipitation increases, and that's why I did not use calcium in my bicarbonate amendment studies. Everything precipitates. Growth on sodium bicarbonate and calcium addition may improve biomass productivities. Lipid production may be facilitated by the addition of extra sodium bicarbonate when nitrogen is when a nitrogen stress is introduced. Still, the grain of salt plot that I showed you, lipid reduction in biofilms is lower than suspended cultures. So for RGd-1, we can see 80%, but I'm looking around 37 to 40%. So the production in biofilms is still lower, but improved from before. With that, I would like to acknowledge the awesome people that I work with. Dr. Brent Payton, who is very supportive and an awesome human being. My committee, Dr. Joseph Seymour, Abby Richards, and Matthew Fields, Dr. Robin Garlock, who was previously on my committee, but was overbooked, but still writing papers and helping. Dr. Robert Gardner, who is dearly missed always. Karen Moll, who is in Santa Fe working on bioinformatics. That is our future project for RGd-1 transcriptomics and genome assembly and differential gene expression to improve lipid productivities and understand lipid production in biofilms. Todd Patterson, Matthew Jackson, Thane, who was an undergraduate in our lab, the Payton lab group, which is pictured here. I added the picture. And the MSU Algal Research Group, the Center for Biofilm Engineering, and of course the funding resources, the Montana Institute on Ecosystems. Thank you for funding me for an entire course of the summer. NSF, DOE provided an initial funding. Church and Dwight, MSU Graduate School, the Fulbright Foreign Scholars Program. Thank you so much for attending.
Congratulations. Thank you for this excellent talk. I'm going to encourage everyone to take themselves off mute and give Muneeb a round of applause. The amount of work that has gone into this is really amazing. And now we have a few minutes for questions, and we have a small group, so I encourage you all to turn your video on and to turn your mute off and dig in.
So I guess I have a question. So these fatty acids that you're creating in your biofilms, how easy are they to integrate into a fuel?
So there are different processes that you can use. Some are quite easy, but where we at MSU are not set up to do them, such as hydrothermal extraction, in which essentially you take the entire biomass and break it down into useful organic carbon compounds. And this reaction is fairly easy to do. It takes about 4 hours, the transesterification reaction. And essentially what you're doing is you're taking the fatty acid and reacting it with methanol to take to add an ester linkage, and your costs would obviously be different with each processing method.
Okay.
That is something to look at for other researchers.
Yeah, cool. And does like the nitrogen that you're diffusing into your biofilm, does that ever get caught up in that process? Like, would that ever be an issue? Are they part of the fatty acid chains, or are they separate, I guess?
Well, the nitrogen, you have to remember, is that they're using it to make proteins. And
Okay.
yeah, so that is where your majority of the nitrogen would be in the cell. And so not an issue for the fatty acids.
Okay, thank you.
Welcome.
Any other questions for Muneeb? Dr. Sandvik is saying goodbye and congratulations.
Thank you.
Well, not hearing any others, I want to thank you so much for making this presentation, and this will be recorded and made available through the IOE website. Usually takes a couple of weeks, so something that you can link into as needed. And congratulations. Keep up the good work. Thank you so much for coming today.
Thank you all for coming.
See you guys. Good job.
Thank you.